Hi everyone, in this video we will look at one of two systems that we will be learning. The first one is called a cylindrical coordinate system. So what I will do is I will only introduce you to the coordinate system, and then when it comes to actually using it with triple integrals, we will do that later. So the first coordinate system that I want to introduce is called the cylindrical coordinate system, and it's very much related to the polar coordinate system. So let's start with recall the polar coordinate system in 2 dimension. The idea there is that even though we have rectangular coordinates, we can create an equivalent. So if there's a point P, and in the rectangular coordinate, this is x comma y, where this is x and this is y, I can create a parallel system where I write this as r comma theta, where r is the distance of this point from the origin and theta is the angle it makes with the positive x-axis. And we know the bunch of relations that connect one to the other. So we have x equals and y equals. X is r cosine theta and y is r sine theta. So that's how we can go from from r theta to xy. And similarly, we have a relation between r squared and tan theta. R squared is given by x squared plus y squared. That's straight up from Pythagoras theorem, and tan theta is given by definition of trig ratio as y over x. Now this same idea, when translated into 3 dimension, in 3D, this gives us a cylindrical coordinate system. So what is that? Now, in our representation of the 3-dimensional axis, we usually put xy over here and z going out of the plane. And the idea is that if I have any point P that's up here in space, what I can do is I can project this down to the xy plane, and I can call this height. That's going to be z. Now when I look at this particular projection of this point here, I can use polar coordinate to describe this. So I can call this distance r, and the acute angle from positive x direction, well, not the acute angle, but the direction, the angle from the positive x-axis being theta. Now when we do this, we get a very nice relation, and the relation is, if we started off with this point P, X, Y, Z, then the relation we get is x is r cosine theta, just like polar coordinate, y is r sine theta, and z just equals z. And on the flip side, we have the same relation, which is r squared is x squared plus y squared, and tan theta is y over x, and z equals z. So basically, all we have done is we have taken the polar coordinate and we have added a third value to it. So it's r theta z, and the height, that is z, remains constant. It's only r and theta that are changing by moving into polar. And this is called a cylindrical coordinate system because, as you can see, the points are actually, they're kind of arranged in a cylinder because you have a circle and a height. So any point has a height z, and it has some radius and some angle theta associated with it. Okay, so let's just look at some examples of converting from one system to the other, right? So cylindrical, if I have a point 2 pi over 3, 1, what would that look like in rectangular, right? So comparing the position, that's r, that's theta, and then that is z. So if I have r and I have theta, I can find the xy. This is going to be r cosine theta, which is 2 cosine 2 pi over 3, which will come out to -1, and r sine theta, which is 2 sine 2 pi over 3, which comes out to √3, and then z is just 1. So this is a point which in the rectangular coordinate system would be -1 in the x direction, so behind, √3 in the y, and 1 in z. So somewhere over here, -1, √3, 1. So if you project this down, it's somewhere there. That's 1, that's √3, and that's 1. Or if you want to plot it directly using the given values of 2, so 2 would mean it's somewhere at a distance of 2, so the projection is distance of 2 and an angle of 2 pi over 3. 2 pi over 3 is more than pi over 2, it's 120 degrees. So 120 degrees from here is on the negative side here, and it's at a distance of 2, and then you go up to get 2 pi over 3, 1. And so this distance is 2 and this height is 1. Similarly, you can be asked to go from rewrite 3, -3, -7 in cylindrical. So now you have x, you have y, you have z. So I will use the relation r squared is x squared plus y squared to get 9 plus 9, 18, and r as 3√2, which is square root of 18. And I have tan theta is -3 over 3, or well, if you're writing the expressions here, let me be consistent. So y over x, which is -3 over 3. So theta is going to be inverse tan of -1. And inverse tan of -1 is going to give me 7 pi over 4 plus 2n pi as a general solution. And z equals -7. Okay, so there are infinitely many choices. And that's because when we go to polar, after the points repeat after every 2 pi rotation. Okay, now let's look at what happens, what are some advantages of this, some advantages of this system. So you recall that we use polar coordinates mostly when we deal with circles because it makes things easier. So, the name cylindrical suggests that maybe this also makes certain figures easy to understand. So the first one is, what is r equals c, which is a constant in cylindrical coordinate. So if r is constant, what's happening is we're looking at all the points which are at some constant distance from the center, and that's going to give me a circle in the xy plane. But r equals constant means that z could be anything. So it means this whole thing just runs up and down without restriction. So this is a cylinder of radius r. Okay, these points here intersecting the x-axis is 0, c, 0, intersecting, this is y-axis, this is x, x-axis is c, 0, 0, and so on. So if r equals constant, we get a cylinder. The next question to ask naturally is, what is r or theta equals constant? So if theta is constant, it means r is changing and z is changing. So once theta has been set to a constant value, something like c, it's not changing, where we are just over here. But z can take any value, so it goes up and down, and r can switch. So r can get smaller and smaller, and for each r there can be vertical lines. In fact, it can go all the way back, and for each negative r, as long as it's on that angle, what we will end up with is a plane. If you connect all of those lines, this will become a plane. So when you keep theta constant, you get a plane that goes through origin and is at an angle of c, or whatever the constant is. And the last one is simple. What is z equals c? Well, that doesn't, since z doesn't have a new representation, z equals c is just a regular plane at some constant height. So this is again a plane. Specifically, it will be a horizontal plane. Whereas here, as you change theta, it's this kind of a vertical plane that's gonna keep on rotating. Let's do one last example of just understanding different surfaces. So in this example, it says describe the surface z equals r. Okay, so what we're saying here is we're working with a surface which has the equation z equals r. So the height depends on the radius. And to do that, we will always revert back to the definition. So recall that r squared is x squared plus y squared. So we actually have z squared is x squared plus r squared. And we have seen this before. This is an equation of a cone. So the equation of a cone in cylindrical coordinate system is a little more straightforward. It's just z equals r. And you can see the height of this is going to correspond to the radius of whatever circle that we are in at that point. So that's it for the cylindrical coordinate system. We'll come back to this, but when we come back, we will be looking at doing triple integrals using cylindrical coordinate.